let us start. Let me remind you what we did last week in the pre-recorded lecture. So there was this lemma about the canonical cycle notation, which is canonical cycle notation, which so you take a permutation, you write the cycle so that each cycle starts with the maximal element, and these maximal elements increase left to right. Yeah, by the way, feel free to turn on your videos. And then the lemma was that if so you have a map f from Sn to Sn, which forgets the you take a permutation W and write W in Sn in canonical cycle notation, and then forget the parentheses, right? So yeah, if you have cycles 5, 2, 4, 1, 6, 3, 6, 3, maybe 9, 8, 7, something like this. Yeah, then you just forget the parentheses, and you get a permutation in one line notation 6, 3, 9, 8, 7. So that if this is W, then this is f of W. Just a very stupid map, which happens to work in the sense that it gives you a bijection. And so today I want to start with discussing why is this map useful. And it's useful because it allows you to relate things in an unexpected way. So, and the first corollary I'd like to mention is sort of trivial. So remember, in the proof of this lemma, we introduced the left to right maxima. So if you have a permutation V in Sn, then Vj is a left to right maximum if it's bigger than all the previous elements. If Vi is less than Vj for all I less than j. And so the bijection, the proof of the reverse bijection was trying to find these left to right maxima and then inserting the parentheses in left to right maxima and then inserting the parentheses in the corresponding way. So in particular, we get a nice corollary, which is that the number of permutations V in Sn with exactly k left to right maxima is equal to the number of C of n comma k, which is the number of permutations with exactly k cycles. And so yeah, this kind of follows trivially from this bijection, right? If you have a permutation with k left to right maxima, then you apply the inverse of this map and you get a permutation with exactly k cycles. So yeah, in this sense it's trivial. But if I started with this claim, right? So let's say forget everything else. I can define cycles and left to right maxima in like 5 minutes, and then ask you to prove this bijectively or in any other way, and it's tricky. So without that bijection, that would be tricky. But let me mention something that's even more unexpected, and I think it's sort of pretty cool claim. Again, it's Right now it's about only cycles and permutations. So here's the claim. Let's say you have two elements, I and j. So let's say I is not equal to j, and then I want to ask, what is the probability? What is the probability? So let's say I choose, okay, so fix I and j. Fix I and j, and then choose a random, uniformly random permutation W in a Sn. Then the probability that I and j belong to the same cycle of W. Can you guess what the answer is going to be? Maybe I should even try an example. So let's say we look at this example here. Let's say I and j are 1 and 2, and then they belong to the same cycle here, and here, and here. So that's 3 out of 6. And what about 1 and 3? Well, I mean, 1 and 3 also 3 out of 6. I mean, it's pretty easy to see that the result does not depend on the actual choices of I and j. But anyways, any guesses? What is going to be for arbitrary n? One over n minus 1. Ah, that's interesting. So indeed, here it's you would think it should go to 0, right? As n goes to infinity, usually there's more and more cycles, so 1/2 feels too obvious. Okay, yeah, the answer is 1/2. The answer is 1/2, and which is surprising. So in other words, permutation with long cycles kind of dominate, I guess. Anyways, yeah, that's the... I'm not sure how to quantify it and how to explain it in down-to-earth terms, but mathematically it's very easy to prove using this Fourier transition lemma, which I think is kind of neat. So yeah. Here's the proof. The first claim is that isn't it either ij in the same cycle or not, therefore 1/2. Well, I mean, there is 2 options, but having 2 options doesn't mean that the probability is 1/2. Like, I could say, what's the probability that 1, 2, and 3 are all in the same cycle? They're either all in the same cycle or not, but the probability is not 1/2, right? It's 1/3 in this case. So yeah, you have to be careful with the probability. Is you take the number of permutations where they belong to the same cycle and divide by n factorial. That's the official definition of probability in this case. Does that answer your question, or 1, 2, 3 has 3 elements, therefore 1/3? Well, that's actually interesting. I don't think that's true in general. Let me see if I can... Yeah, I think that's going to be in your homework problem. Yeah, I mean, so you're saying for any k elements, the probability is going to be 1 over k. And that's a nice conjecture. I think it's going to be in your homework. Some variation of this. Yeah, but I mean, that's a good conjecture. But yeah, let's see what... I mean, how would you prove it even for 2 elements? That's already kind of tricky, right? You can't just say, therefore 1/2. Maybe I should try. Should I try 4? No, 4 is too much. Or maybe I can try. Okay, let's see. No, I can't. All right, never mind. Yeah, that for 3 elements, it's going to be in the homework. Okay, so here is the proof. The first step is to observe that the problem is symmetric. So the answer does not depend on the choice of I and j. Answer does not depend on I and j. Right, because you can relabel all the elements and then the cycles are going to be the same. So, but for our problem, it's going to be the way we're going to solve it is we're going to choose specific I and j. So I'm going to choose, so I'm going to break the symmetry. And what I'm going to do is I'm going to choose I equal to n minus 1 and j equal to n. So, okay. And now what the trick that I'm going to use now is this bijection here. So I want to apply the inverse of this map. So let's say maybe let's say maybe I choose a random permutation v in Sn. And then let W be f inverse of v. So v is uniformly random, f is a bijection, therefore W is also uniformly random. Element of Sn. So so let's see what if you want n minus 1 and n to belong to the same cycle of W, what does it mean in terms of V? How does it translate under this map F? I comes before j, I and j not in the same cycle. Right, yeah, that is absolutely correct. And it only works when I is equal to n minus 1 and j is equal to n. So n minus 1 comes, let's say, before n in v, in the one-line notation for a v, if and only if. So it comes before everything after n belongs all to the same cycle, right? N is always a left-to-right maximum, and whatever is after that is not a left-to-right maximum. So if n minus 1 comes before n, then they are in different cycles. And if it comes after n, then they are in the same cycle. Well, so the answer is, let's say I choose an arbitrary I and j. Then what I can do is I can relabel all the. Okay, let me try to explain why does the answer not depend on I and j. For example, let's say W is some permutation. 1, 2, 3, 4, 5, 6, 7, 6, 2, 7, 1, 4, 5, 3. Then I can choose I can relabel all the elements. I can relabel maybe. So let's say you give me I and j. Maybe I is equal to 1 and j is equal to 4. And then I want to relabel 1, 2, 3, 4, 5, 6, 7. I want to relabel 1 by n minus 1 and 4 by n. And then I choose maybe some other 2, 3, 1, whatever, 4, 5. So if what I'm going to do now is I'm going to take this 2-line notation, and I'm going to replace every every integer here I see here by the corresponding relabeled integer. So what I get is, after I relabel, I get, instead of 1, I get 6. Instead of 2, I get 2. Instead of 3, I get 3. Instead of 4, I get 7. Instead of 5, I get 1. 6 is replaced by 4. 7 is replaced by 5. And similarly in the bottom, 6 is replaced by 4. 2 is replaced by 2. 7 is replaced by 5. 1 is replaced by 6. 4 is replaced by 1. And 5 is wait, what's going on? 7 is replaced by, sorry, am I confused? I should be looking at this row and relabeling it using this permutation here. So, okay, let's see. 1 gets replaced by 6. That is true. Now 4 is replaced by 7. 5 is replaced by 1. And 3 is replaced by 3. Okay. Yeah. So, and then I can, so I relabel, and then I can sort the top row to get back a one-line notation of the permutation. 3, 4, 5, 6, 7, and whatever. 1 goes to 7, 2 goes to 2, 3 goes to 5, 4 goes to 1, 5 goes to 3, 6 goes to 4, 7 goes to 6. And I get a new permutation where now I is equal to 4, and well, now I is equal to n minus 1, and j is equal to n. And the point is that the cycle structure stays the same, right? I just replaced all occurrences of 1 with occurrence of 6. So you kind of relabel all elements of your cycles, but the actual cycle structure does not change. So well, maybe I should write down the cycles. I think that was also in one of your homework problems, actually. What I'm doing is I'm conjugating W by this permutation here. So cycles of W, 1 goes to 6, 6 goes to 5, 5 goes to 4, 4 goes to 1. That's one cycle. And another one is 2 goes to 2, and another one is 3 goes to 7, and that's it, right? And then cycles, let's say this guy is here, this is W prime. Cycles of W prime are 1 goes to 7, 7 goes to 6, 6 goes to 4, 4 goes to 1, and 2 goes to 2, and then 3 goes to 5, 5 goes to 3, then I is 6, and j is 7. Yeah, so I was 1 here, and it became 6, and j was 4 here, and it became, oops, again, I should be looking at the relabeling. So I was 1 here, and now it's 6, and j was 4 here, and now it is 7. And indeed, I see that, oops, I see that 6 and 7 are in the same cycle here, just as 1 and 4 were in the same cycle of W. And more generally, you can get from the cycles of W to the cycles of W prime by relabeling, by just replacing each, like replacing 1 by 6 and 2 by 2, and etc. Right. Does it make sense, or is it completely confusing? Okay, thanks. Yeah, the point is you can draw a permutation. Yeah, let me explain it in a different way. You can take your W here, right? Which let's say W looks like this. And you can draw it as a directed graph. 1 goes to 6, goes to 5, goes to 4, goes to 1, and then 2 goes to itself, and then 3 goes to 7, 7 goes to 3. That picture here is the same information as W, right? But then I can look at these numbers and the cycle structure of W doesn't change if I permute these numbers in any way I like. I can just swap 1 and 2 in all such pictures, and then the distribution on W's is not going to change. So in other words, I can sort of treat these as just some vertices, I guess. Yeah. Anyways, all these arguments which say just by symmetry something is true, they are sort of hard to explain precisely. But the precise statement is that if you take a permutation, then you conjugate, then the action on the cycles. Yeah, I think that's in your upcoming homework, the one due Friday, unless I'm wrong. All right, anyway, let me know if I'm not being clear. Otherwise, let me try to. But I mean, you're correct that even though the original statement does not depend on I and j, the proof depends on them very heavily. So it makes you question the validity of that step. n-1 and n are in different cycles of W. So in particular, the probability of this event is 50%, because you can reverse the permutation, and therefore the probability of this event is also 50%. So the cycle doesn't change after relabeling, i.e. cycle 2 is fixed. Well, if I relabel 2 by something else, if I relabel 2 by 5, then this becomes a cycle which consists of a 5. Okay. And yeah, that's the end of the proof. And yeah, sorry for not being very clear with this relabeling stuff. But if you just try to think about it, like, the answer should not depend on I and j just because it's the whole problem. Yeah, I think this picture is the best explanation. You can first choose the arrows, and then you can choose the labels in any way you like. Yeah. Anyways, I guess I should. All right, yeah, let's just move on. But yeah, I think the actual claim is pretty nice, and if I ask you to prove it just from the first principles, it's pretty tricky. All right, so and that's basically one last thing I want to talk about in the permutation world is I want to go back to generating functions. Generating functions. So I want to use the results from the previous lectures to write down some generated functions, and one other thing I want to do is I want to mention a permutation version of the exponential formula. So first, let me remind you the exponential formula. Right, you denote by pi of bracket n the set of set partitions of bracket n, and then the exponential formula tells you that if you have two sequences, and let me even, yeah, I'm gonna even try to split screen and exponential formula. So you have a sequence f of n, and f of 0 is equal to 0. And then you let h of n to be another sequence, be given by h of 0 is equal to 1, and h of n is the sum over all set partitions S1 up to Sk pi of bracket n, and then you take f of the size of S1 times f of the size of S2, etc., f of the size of Sk, and so you define h of n in this way, and then the exponential generating function of hn is given by h of x, and it's the exponential of the exponential generating function of the f's, which I'm going to write down explicitly. F of n times x to the n over n factorial. Okay, so what I'm going to try to state on the right is another theorem, which is the exponential formula permutation version. And I start with the same data, so let f of n be a sequence. F of 0 is again equal to 0, but now I'm gonna do something slightly different. So I'm gonna let h of n be a sequence defined by h of 0 is equal to 0, and h of n is the sum. Now it's going to be the sum over all permutations in Sn, and I'm going to take the sum over permutations, and I'm going to split each permutation into cycles, and then I'm going to apply f to the size of each cycle. F of the size of C1 times etc. times f of the size of Ck, where C1 up to Ck are the cycles of W. And then the conclusion is that the exponential generating function of h of x, is the exponential of the sum over n from 1 up to infinity, fn times x to the n, but now here I'm going to divide by n. So the difference is that n factorial versus n. That's the only difference between these two formulas. And and this is mostly useful when you, let's say you want to compute some generated function. You're allowed to take maybe permutations with cycles of some given length, right? Maybe you have a set of lengths. Then f of some cycles is going to be 0, and of the other sizes is going to be equal to 1. So that's how you are going to apply this formula here. And I'm going to give you some examples, but yeah, let me know if the statement is clear or not, and I guess I'm going to try to prove it right now. And the proof is going to be, I'm going to deduce the permutation version from the usual exponential formula. So here's the proof. It's very short, I guess. So I'm going to introduce another sequence. So the setup is, as on the right hand side, I'm going to convert f of n into another sequence, g of n, and my goal is to relate this to this. So what I'm going to do is I'm going to set g of n to be just equal to f of n times n minus 1 factorial. Okay, then so why is this nice? Well, the reason is that then if I apply my definition here, right, so h of n is the sum of, let me even copy So h of n is given by this formula. But then these cycles, they form a set partition of bracket n. So if I just sum over the corresponding set partitions, S1 all the way up to Sk in pi of bracket n, then each set partition appears many times in this formula. Well, how many times? I have to, if you just give me a set partition, then in order to make it into a permutation, I have to pick a cycle. I have to cyclically order each block of my partition. So I have to basically multiply by the size of each partition by like the size minus 1 factorial. That's the number of cyclic structures. So in other words, that's right. The reason is that because g of the size of Si is equal to the number of cyclic orders on Si, which is the number of cyclic orders of Si times f of the size of Si. And this guy is the size of Si minus 1 factorial. Okay? So that I'm just doing a very simple transformation to my sequence, and then because if I look at this formula here, I see that it's exactly the same as the formula on the left, except that this one has f and this one has g. So in particular, the usual exponential formula applies, and what I get is this conclusion here. So thus the exponential generating function of h is given by the exponential of the sum n greater than or equal to 1 g of n x to the n over n factorial. And then if I plug in this formula back into this formula here, then I get the exponential of the sum over n greater than or equal to 1 f of n times x to the n over n, because n minus 1 factorial here cancels out with the n minus 1 factorial here. Maybe an explicit example for g equal to f times n minus 1 factorial. I mean, if so that's the end of the proof. If you, I'm going to give examples, but I mean the example is you just have one sequence and then you multiply each nth value by n minus 1 factorial. So maybe an example is maybe f of n is equal to 1 for all n, then g of n is equal to n minus 1 factorial for all n. So I don't know if that's, yes, that's just an example of what I'm doing. Okay. And actually, yeah, this I think is going to be the first example. So this is kind of an interesting example because yeah, let's see what happens in this example. So I set f of n to be equal to 1 for all n greater than or equal to 1. So let's just apply directly this formula here. I have h of n is the, well, yeah, let's h of n is whatever it is, right? It's h of n is this formula here, which every term is equal to 1, right? So that's the sum over w and Sn of just 1, which is n factorial. On the other hand, I can apply the formula. Right? I can say that h of x is equal to the exponential of the sum over n greater than or equal to 1 f of n x to the n over n. which f of n is equal to 1. So it's just the sum of x to the n over n. And that is the generating function of the logarithm of x with some extra twist. It's the exponential of the, I think we did this particular sum before, and that's negative logarithm of 1 minus x, because all the signs are plus 1 here, so you get minus x. And now I can take the exponential, so the exponential of the logarithm would be 1 over 1 minus x, but then the minus sign takes it to the 1 over 1 minus x, which is the sum over n greater than or equal to 0 of x to the n. Or in other words, it's the sum of n greater than or equal to 0 of n factorial times x to the n over n factorial. And h of n is the coefficient of x to the n over n factorial. So everything is consistent. I have computed n factorial in 2 different ways. So that's probably not surprising. And any questions on this example before I do a slightly more interesting one? All right, yeah, let's try another one. This one is, because yeah, we already knew it was gonna be n factorial, but now let me try to compute involutions. So what is an involution? And I already mentioned fixed point free involutions. Now let's talk about general involutions. Definition: a permutation W in a SN is an involution if it squares to the identity permutation. So it's a permutation such that if you apply it twice, you get back to where you started with. Or yeah, another characterization is that, in other words, all cycles of W they have length 1 and 2. 1 or 2. So question is how many involutions are there? So the number of involutions in SN, and I mean it's very much not clear how to count these, because the cycles could be of length 1 and 2. Then you can't really, you would want to count maybe set partitions of size 1 and 2, but that's not exactly clear how to do this. So I'm going to try to do this using this exponential formula permutation version. So here is the claim. Number of involutions is equal to h of n, which is by definition is the sum for I from 0 to the floor of n over 2 of 2i minus 1 double factorial times n over 2i, and choose 2i. So in other words, you take these binomial coefficients for all possible values of I for which this is non-zero, and then you take the corresponding double factorial, where there is only one problem, which is for I equal to 0, where for I equal to 0, I get -1 double factorial. And by definition, -1 double factorial is, I'm just going to set it to be equal to 1. So maybe I should try to count when n is equal, yeah, let me make it into a proposition, and maybe this should be an example for n equals to 3. So for n equals to 3, I would like to count permutations, which are involutions. And so here are the 6 permutations. And you can see that if a cycle has length 3, then it's not an involution. You apply it twice, then the cycle shifts by 2, and it doesn't get back to where it started. So there are the number of involutions just by direct counting is equal to 4. These 4 are the involutions. Identity plus all possible transpositions. So, okay, how do I apply this formula here? Let's see. N over 2 floor is equal to 1. So I have a sum from 0 to 1. H of n is equal to the term for 0, -1 double factorial times n choose 0 plus 1 double factorial times n choose 2. And the answer is 1 plus 3, which is 4. Okay, so let's try to prove this. The idea is to apply this formula again, right? Because it's very clear that we should apply this formula because of this description here. You only want to allow cycles of length 1 and 2. Whenever you have condition on length of your cycles, that means you can apply this formula here. And in particular, what should be, let f of n be given by, maybe somebody can tell me what should I take for f of n? What number sequence should I take? F of n is 1 if n is less than or equal to 2 and 0 otherwise. Yeah, thank you, that is correct. So f of n is, well, it's 0 if n is equal to 0, 1 if n is equal to 1 or n is equal to 2, and 0 otherwise. Yeah. So I guess I could have just erased this line here. Anyway, so in particular I can compute I have to compute this generated function here. So h of x is equal to the exponential of f of 1 times x to the 1 over 1 plus f of 2 times x to the 2 over 2, and that's it. So that's the exponential of x plus x squared over 2. Okay, and how do now I want to compute I want to expand this as an explicit series. So the easy way to do this is to observe that the exponential of a plus b is equal to exponential of a times the exponential of b. This is the exponential of x times the exponential of x squared over 2. And now I can expand each sum. Let me try to peek at the proof. Yeah. So you just expand each of the two exponentials. K from 0 to infinity, x to the k over k factorial. And the second sum is I have to plug in x squared over 2 instead of x into this sum. So it's the sum over I greater than or equal to 0. Let's see. X squared over 2 to the I over I factorial. And if now let's see. So x squared to the I is x to the 2i. X to the 2i, and on the bottom I get 2 to the I times I factorial. So, and now I can just multiply. I know how to multiply 2 generated functions, just the same rule as for multiplication of polynomials. So in particular, I had a specific, the coefficient of x to the n over n factorial is what? If I look at this sum, right, let's sum over I, because I contributes x to the 2I. So if I want the total degree of x to the n, then I has to go from 0 to the floor of n over 2, because that's all the possible things you can get from the second term. Okay, and then you get x to the 2I, right? X to the 2I times over 1 over 2 to the I times I factorial. And then you have to get the rest of the x's from the first sum. So the first sum contributes. Yeah, let me even write the value of x. So x to the 2I over this, and then the second one gives me x to the n minus 2I over n minus 2I factorial. But now if I want to extract the coefficient of x to the n over n factorial, I have to multiply by an extra n factorial. And then I have to erase the x's, because the x's are, they correspond to x to the n. So 1 and 1. And that's it. So now I have to transform the sum from 0 to floor of n. Like the rest is just algebraic manipulations. I want to turn this guy into a binomial coefficient. So 1 over 2 to the I times I factorial times n factorial over n minus 2I factorial. And then I want to add an extra 2I factorial. So I have to multiply by 2I factorial. Now this guy is a binomial coefficient. Sum I from 0 to the floor of n over 2 of n, choose 2I times 2I factorial over 2 to the I times I factorial. And finally, from one of the previous lectures, recall from I think it was the previous lecture, that 2I factorial over 2 to the I times I factorial was nothing but the 2I minus 1 double factorial. I minus 1 double factorial, and choose 2I. And that's the end of the proof. And so I guess this is actually you can try proving this bijectively or by some direct counting argument. That is not exactly easy to do. But so that's a nice application of the exponential generated function formula. And okay, I have 2 minutes left. Yeah, I think I should just stop here. So if you have any questions, let me know. If not, I will see you all on Friday.